So now let's see how you can perform some energy trade-offs, energy power trade-offs, using more than just voltage and frequency in your toolbox. You can use parallelism, you can use pipelining and time multiplexing, right? So the main counterintuitive idea that you need to get in your head is that running things in parallel can reduce energy, and we will see how, right? So the way we're going to look at that is we're going to consider having parallel copies of hardware or pipeline copies of hardware. So different parts of your hardware are busy doing useful work, right? You will see that if you try to resource share too much, you might end up adding to your energy burden. And the thing you need to couple with parallelism and pipelining is the idea of voltage scaling, so we can address other sort of metrics like energy delay product or EDP or energy delay squared product, which apparently is more commonly used in industry. Okay, so let's try and walk through a couple of examples, right? So here you have ax squared plus bx plus c executed by this circuit shown by this red box. I'm telling you that this circuit takes E amount of energy and a D amount of delay. If I have to get this circuit to solve a problem with n possible values of x, I'm going to need n times E amount of energy and n times D amount of delay. So the energy delay product will be n square E times D. So far so good. The exact values of E and D don't matter. This is the setup. Now I'm going to parallelize this problem across, let's say, P copies of hardware, right? So I have the budget to make a big chip. So I'm going to replicate my polynomial circuit. Now every copy gets 1 over P fraction of the original array of n inputs, right? So now the energy required by one of these circuits is n over P multiplied by E. But I have P of these circuits, so that P term cancels out. So my total energy is unchanged, right? So just parallelizing something doesn't magically reduce energy by itself, right? So total energy at this point is n times E, but my delay has reduced, right? So now I need only 1 over P amounts of time to run my problem. Makes sense. I've parallelized my problem, so I need less time to solve my problem. My energy delay product is now n square ED divided by P. So it's improved by a factor of P. Now an interesting thing that should tickle your brain right now is energy hasn't changed, delay has changed. What can I do to actually get an energy improvement here, right? And the answer is voltage scaling. Let's say the customer that you're designing this circuit for doesn't want your circuit to run this fast. Maybe they're happy with it running at the speed at which the sequential circuit was working, right? So remember, T is inversely proportional to VDD, energy is proportional to VDD square. So maybe I could reduce voltage by a factor of P. Now, this is all theoretical calculations. You might not be able to reduce voltage by a factor of P, but let's say you can. Your delay will increase by a factor of P. So now the amount of time it takes will go back to n times D, right? So you had that factor of P improvement that's now taken away because of delay, transistor delay increase. The energy that you needed will reduce by P square, right? Because you have lowered the voltage. So delay is the same, energy is reduced by a factor of P square. Compared to the sequential case, you're now P times better in terms of energy delay product and P square times better in terms of just energy, right? So you walked away by reducing voltage by a factor of P with a P square reduction in energy while taking the same amount of time to compute as before. So parallelism can help you recover energy if you're willing to slow down your parallel hardware to match the speed of your sequential hardware. If you don't want to do that, there are intermediate design points that you can look at as well. So you won't get the full P square benefit of energy, but you can still walk away with some non-trivial benefit, right? So that's sort of step one in this journey, is to use parallelism. Step two is pipelining. So with pipelining, the idea is, let's say you have these three stages. You're doing ax squared first, then you're doing bx, then you're finally adding c. You have a bunch of multipliers and adders spread across these three stages. When x changes, the first thing you will do is update ax squared, and then that result will be added to bx and so on and so forth. And you're waiting until the whole chain of operations is finished before you change x. So parts of the hardware have already finished computing ax squared, might have already finished computing bx, but I'm just keeping them powered on for no reason, right? So what pipelining does is it helps you address energy and delay differently, right? So what it helps you do is it helps you split tasks in a different fashion. Each stage here is going to require E1, E2, E3 units of energy. Each stage is going to require D1, D2, D3 units of delay. So my energy delay product is going to be sort of defined by the E and D terms, right? So I'm going to have energy E1 spent by the first stage being used for D1 plus D2 plus D3 amount of time, right? So it's staying on for the entire duration of computation, even though it only needed D1 units of time to work. Same for E2, same for E3, and let's for simplicity assume that all E's and D's are equal. The energy delay product is going to be 3 square times ED, right? Which is number of stages squared multiplied by E multiplied by D. That's for the unpipelined case, when each block of hardware has to stay powered on for the entire duration of computation. Now, if you pipeline the design, your delay will now just be the max of the individual stage delays, right? So you don't need to keep the entire pipeline powered on for the full duration. You just need to keep it powered on for the worst case stage, right? Now the total energy again is unchanged, ignoring the energy required by the registers right now. Delay is max. So the energy delay product is going to be the sum of the energies required, but the time required won't be the sum of the delays. It'll be the max, right? So now again, set all E's and all D's to be equal. You will see that the energy delay product is 3 times ED, which is 3 times better than the unpipelined case. And we can use the same trick again, right? By scaling voltage by number of stages, we can match the delay of my pipeline design to that of the unpipelined design and recover the quadratic factor in energy that I promised you, right? So here you have 3 stages. Assuming all E's and D's are equal, I can scale VDD by 1/3. Delay will increase by a factor of 3. My energy delay product will be 3 times better than the pipeline scenario where VDD didn't change, right? So you walk away with a 9x sort of improvement in energy per stage, but you're back to square one in terms of delay. And if that's an acceptable trade-off, then yeah, that's something that you need to be thinking about. Okay, let's switch gears and look at activity rates, right? So we've tried to be cute about using parallelism and pipelining, but now we need to start thinking about ways to reduce the amount of toggles in your circuit. Now, this is something you can control in Verilog, right? Which is why this analysis is important. Voltage and frequency, you cannot really control in Verilog. Those are system level parameters. But for activity, right, you can actually add some gating functions that will help you reduce how many times the signal toggles. So remember, power is proportional to alpha FCV square. So you want to try and reduce that alpha term to the extent you can. And the simplest trick in the book is to use valids judiciously, right? So if you have a data valid signal along with your wide 256-bit wide data bus, you can add this if condition. So what this does is it only updates data if required, right? If valid is 0 and there's garbage data on input, why propagate that garbage data down your circuit? Because it will consume unnecessary amount of power, right? So you can add that if condition, and that's going to reduce spurious transitions on the data signal, which then goes into that compute function, right? Which might be a complicated function. If the data values are stable, right? If valid goes 0, the data value will be the same as the previous cycle. So no further 0 to 1 or 1 to 0 transitions will go through the circuit, and the dynamic component is taken out entirely, right? So here's an example of how we compute it, right? So the clock is at the top and ABCD signals run at half, 1/4, and 1/8 of the rate, and D never changes. So we can compute alpha as counting how many 0 to 1 and 1 to 0 transitions happen divided by number of cycles. So in this case, alpha toggles at every clock edge, so its activity factor is 1. B toggles at half, C toggles at half of that. D is constant, so the alpha in this case is 0. If you have AND gates and OR gates where one of the inputs, the controlling input, is the right value, you can propagate, there's no activity in the output, right? Even if one of the other inputs is a variable. So for example, if you AND with a 0, the output is a 0. If you OR with a 1, the output is a 1. So since you can prove that the outputs are going to be constants, you can compute the activity rate on these signals upfront. Right? So let's take an example with our AX squared plus BX plus C circuit. Let's assume that A, B, C are constants. So alpha A, alpha B, alpha C is 0. Let's assume that X is changing once every 2 cycles. And let's do a step-by-step propagation of activity, right? So the first thing we can prove is, the output of the multiplier will have an activity factor of 0.5, which is the sum of the activities of the inputs. The reason we do a sum is because either change can cause an output change. And we can propagate it one more time. And then the second time we propagate it, the activity can be 100% because you have misaligned changes to x and y1. If they arrive at the same time, they might cancel out, but they may not, and quite likely they won't. So you might end up with sort of 100% activity rate, and then that's what you get at the output. Even though you started with only 50% activity on x, you might end up with 100% activity on y. And this is sort of an upper bound. It might not happen, right? Things might be better than this, depending on the actual values of x and y. But this is what we can prove, right? Using this simple analysis. There are more sophisticated analyses, but this is the simplest one. Okay. Right. So now if I know that one of the inputs is a constant, 0, anything multiplied by 0 is a 0, so I can propagate that information differently to reduce the bound on how active output y can be. So that y0 term is killed off, y1 term is killed off for activity. So y2 is the only term that can change as x changes, and that's what we're going to end up with. Okay, so what we saw in this lecture was the introduction to energy and power, very, very fast one. The implications are obvious, right? We live in a world that's heating quite rapidly, so we need to control the amount of power required by compute. We increasingly are spending a lot of power on static components, right? So we need to start thinking about how to manage that. There are dynamic components that also can be controlled by managing activity rates and updating your Verilog. And there are voltage frequency games you can play in conjunction with pipelining and parallelism to get more efficiency out of your design.